Great. Now that the break is over, we'll go further into our transformer architectures, because so far I told you very much about the components that make up the transformer layer, but there were a lot of questions in the break basically foreshadowing what is now to come, because I never talked about how are we even enforcing these representations to become better. It was just, I talked about the components, but I didn't say about how are we going about this. How are we modeling language? How are we producing language? And how are we learning to produce language? Well, and here the idea, and I really want to, thanks for the questions in the break, because this clarified to me that some people here think that we're doing these language models to solve very, very, very specific tasks, but the paradigm is a little bit different. We're learning language, and I'm saying everything about language that you can learn in the first place, and after we have learned language and have gotten language understanding, then we can think about how to make these transformers do very, very, very specific tasks. And with the tricks from 2020, you don't even need very much trickery anymore. You need prompting, but more about that later. The idea is that our aim now is to understand language, because if we understand language, then everything that will be presented to the model in natural language will already have good representations that will help whatever downstream task interest we have. So the question is how to learn language by self-supervision. So self-supervision means that we don't have text where people start to annotate it and write labels about it and start to think about it and annotate it. And no, it's just we have text lying around on the internet, and we take that to train on just that with no annotation. That's why it's called self-supervised. And for the simplicity here of the visualizations and the argument, we just assume that our internet-sized data set is composed of just one sentence, namely, the cat sat on the mat. Yeah, of course, there's way more sentences than that, but let's suppose we are just looking at that sentence right now. And how to learn language self-supervised from text. There's mainly two paradigms, and this is the first paradigm that came into being in 2017 and was very successful until 2020, and then another paradigm came about, and I will tell you about that too. But these models are still very much in use out there, especially in low-resource domains like medical applications and so on, so it's very important to talk about them too. It's called masked language modeling. So the idea is to take our training sample, take the cat sat on the mat, and select randomly a subset of 15% of the tokens from this input and mask them. So we replace a token with the mask token. The mask token is a special token that we have defined in our tokenizer. And so let's say the random number generator just shows the cat, the word cat right now, and we replace it with the token mask. And then the task of the model is to unmask this token, to say which of the, let's say, 60,000 tokens that we have in our vocabulary is a good replacement for mask. And it's really a multi-class classification setting. So we just use the cross-entropy loss, which I hope you're already familiar with. And the idea is that we penalize the model, so we increase the loss every time it chooses something other than cat. And if it says cat, we say, you're a good language model, you can go on to the next example. And these architectures that usually trained by mass language modeling are called transformer encoders, or bidirectional encoders, for reasons you will see in the following slides only. And notable examples of such transformer encoders are the BERT architecture. So every time you see BERT, it's the character from the Sesame Street. So every time you see BERT in a name, it's an encoder, usually. Okay, and that's one main way to do it. Another very successful way to do it is autoregressive language modeling. So here the idea is, again, we don't need any annotation about our data set. We're using the data set itself as annotations, namely by teaching the model to complete sentences. So we have the full sentence, the cat sat on the mat, but we pretend we don't have the full sentence and we just have the cat sat. And then the task of the model is to predict what token is likely to come next. This is all what ChatGPT is doing. It takes your input, your text, and it's predicting what is a likely continuation of what this user has given me right now. And it's again a classification setting because we have to choose one of the 60,000 tokens from the vocabulary which is likely to come next. In this multi-class classification setting, we again can use the cross-entropy loss function and will use the cross-entropy loss function. And it's called autoregressive because during training, the model kind of eats its own, not during training, sorry, during inference. During inference, the model kind of eats its own output again because let's say it has this, this token the, it says cat, and then the prediction cat will go on into as input, and then the model will predict the next token, and then it says sat, and then sat goes into the input and so on. So because the output becomes the input, is appended to the input, it's called autoregressive. And very notable examples of such transformers that do this are the GPT family, so ChatGPT, GPT-1, however, and they're called transformer decoders or autoregressive decoders for the reason here of autoregression, or causal transformers for reasons that you will see just in the following slides. But yeah, these are the main two ways to do language modeling via transformer encoders, mass language modeling, or transformer decoders, autoregressive language modeling. So now we will get into the details on how exactly do we train and make inference with these models. And for speaking about that, I put here the transformer layer for a last time up on the slides. You need to internalize everything, all the subcomponents, because from now on I will not show all the details of what a transformer layer is composed of. I will just say that we have L transformer layers that will do their job. Yeah. And we have our input, we have our output vectors, and now the question is, how do we even generate language from these L transformer layers? And I will start with presenting the transformer decoder because it's a little bit more simple. I don't know why I chose the transformer decoders, but we say how do transformer decoders produce language? They look at the language that was already in the input, then do the transformer layer computation, so apply self-attention, of course positional embedding, self-attention, multi-layer perceptron, compute all these representations here, and then based on the output representation of the last token, it applies a linear layer, which again is learned, and it's learned jointly with all these parameters of the transformer layers. And from it, it produces the next token. So I will get into details of how this works in training and inference, because it's a little bit different. So in training, we already have the sentence. Yeah? Sentences are lying around on the internet for us to grab, and we don't care about copyright usually. So we just look at these sentences that are on the internet, and it's a little bit of cheating to try to predict the next token cat if the next token cat is already in the sentence, right? So what people do during training is they set the self-attention score of the future tokens to 0, such that no information flow happens from the future to the present, which we're trying now to predict. So the transformer decoder during training gets the first token, and applies positional embeddings, does self-attention, which is a little bit boring with just one token, and then applies the MLP, produces hopefully a better representation from which we then can apply a linear decision, a linear layer, which will then map to a vector that is as high dimensional as there are tokens in the vocabulary. So if there are 60,000 tokens in the vocabulary, this is a 60,000 dimensional vector. And from this, and these entries of such a vector are called logits. They're called logits because then they will go into the softmax function that will map all these logits to values between 0 and 1. And the values between 0 and 1 for all of the tokens in the vocabulary, we will also sum up to 1. That's why we usually can interpret them as probabilities and call them probabilities. Okay, and so all of this happens in a so-called forward pass, and then we have to think about how do we compute a loss function to then update the parameters to do better next time when we see such an example, okay? So we need to compute a loss function, and as I was saying, it's just a multi-class classification. We're doing just cross-entropy. Really, it's nothing more. It's just a cross-entropy for deciding which of the 60,000 tokens of the vocabulary to take. So basically what we do is we look at so here when we're trying to predict cat, that's what we're trying to do, we predict cat, we look at what what is the probability that the model outputted for cat, and then we penalize it if that assigned probability is not 1. I don't know if you're more fluent in maths or in Python, but I think in Python code some things become very clear, so that's why I've taken the liberty to write some Python here. Namely, I mean, what happens here? This is a cross-entropy function. The idea is that we are trying to predict cat. And let's say that here, for simplicity reasons, I didn't have time to say to put 60,000 or space to put 60,000 entries, so I just say our vocabulary is 5 long. And cat is our second token in the vocabulary. It could be any position, but it just happens that cat is the second token in our vocabulary. So as an expected probability, we put here a 1 because we see that cat is in the training example. So we put a 1 for the cat and put 0 for everything else. That's the expected distribution to which we want to go to. And this is, the Q is the distribution that the model has outputted over here. And the model said, okay, 0 for 1 for the first token in the vocabulary, 0.6 for cat, and some other values for the other tokens. And this loss function basically looks at whether this is a 1 or not. And if it's not a 1, it will get a high loss function, and it will be minimal if here we have a 1. Now the question to you is, why are we looking just at this, at the cat token, to enforce it to be 1, and why are we not looking at all the other 59,999 tokens and do something about them too to enforce them to become 0? Why are we doing this, except of course saving computation? It is much simpler to do it in at once to compare to do one comparison instead of doing 60,000 comparisons. So yeah. Exactly, perfect answer. So 10 points. So exactly, I would just repeat it loud for, I guess, the camera and for everybody else. Here, these Q probabilities, they don't come out of nowhere. They come out of the softmax function. And in the softmax function, all these values will add up to 1. So if in the ideal case this is 1, everything else will be 0. So it automatically pushes. So if it has to push this one up, everything else will go automatically to 0, and we save a lot of computation time by not doing 60,000 comparisons and just doing 1. And this is how the supervised loss, namely the cross-entropy loss, looks like for transformer decoders. Okay, so we computed the loss function, we have a loss value, and now with it, we can go and do backpropagation and update all our learnable parameters. And when I say all our learnable parameters, I mean all of them. It's really an end-to-end training that happens here. Not very much to train about the softmax, but we can train the parameters of the linear layer. So we have computed here the loss function. We go to the linear layer, do updates, then go into the transformer sublayers, which would be first the multi-layer perceptron. We update all the weights over there. Then we go to the self-attention learnable parameters, namely the query, key, and value producing matrices. We update those too. And after we have update self-attention, we go to the next layer and the next layer and so on. And after we have finished with the transformer layers, we go to the positional embeddings if we have decided for learnable positional embeddings. And anyway, in any case, we go to the semantic representation of the, and we'll update the semantic representation of the, but not the semantic representation for any other word other than the, because that was what happened now during training. Yeah, and very important, and that's why it's called causal attention, and that's why it's called a causal transformer. Self-attention here for the future is set to 0, such that we don't cheat. You know, I mean, we try to predict the future. We shouldn't look into the future. Good, and after we have done this, we have updated our parameters. We can get on to let the model parrot the next token, namely cat. So it doesn't matter what the model chose. As a highly likely vocabulary token here. The token at initialization is anyway stupid. It will not do good choices. We pretend the model did a good choice, so we let it now say, okay, pretending you had the cat, now let's try to predict the next model, next token, namely sat. So we do our transformer layers where attention now is more interesting because it looks at the past, and we will apply the same linear layer that we have over here. So now the linear layer is not it's not a different layer. It's the same weights that we have updated over here. We use now over here, map to the logit space, then map via the softmax to the probability space, compute the loss function, and we do this over and over until we have finished our sentence, our training sequence. And that's a transformer decoder with causal attention. It predicts the next token. Does this learn language? Is this a good way to learn language? Because I was saying that we want to do all this to learn language, and after we have learned to understand language, we can do everything else. I would say it is a good way to do language, to learning, and it's a little bit unintuitive, and it will not work at scales that are very small. So you have to go at Wikipedia size ++ to actually have these things happen. But after you do this over and over and over on larger scales than Wikipedia, you and you try to do the following thing. So let's say a sentence somewhere on Wikipedia says, or it doesn't have to be Wikipedia, it could be my website. It says, I will grab this bottle of water, and I'll keep it in my hand. I will open my hand, and the bottle will, and I have to complete fall. Yeah. So if I have to complete fall, I think as a language model, I've done a good job of knowing what the world, a little bit how the word works, because I didn't say it will fly away. I didn't say it will break, okay, maybe it will break, but I didn't say anything that's impossible. I said fall, and to predict fall already means that I have understood something about language, because language talks about the world, and we try to predict language, but by transitivity, because language talks about the world, we're trying to predict language. So by predicting language, we will eventually learn something about the world, because language talks about the world. So at very large scales, this is a very good way to learn about language by trying to predict the future token. This is what transformer decoders do. And at inference, it looks a little bit different, because at inference, when, you know, I want now, as a user, to let the model complete my sentence or continue my sentence with another sentence. I don't have the future. So here I cannot say the cat sat on the mat, because I don't have this future. I will replace it with a special token called the pad token, but it doesn't matter what this token is anyway, because self-attention will mask it, because I will not peek into this useless future anyway. So, and then during inference, it happens everything what happened during training, just without backpropagation. Namely, we have this token the, we apply our transformer layers, our linear layer, we do the softmax, and then our model will predict a probability distribution over tokens. Okay? And now the question is how to choose from this probability of distribution over tokens what the next token should be that I will accept as a prediction. And this is something called decoding. And there's many decoding strategies, but there's a very simple decoding strategy. We could just do the argmax here and choose the next most likely token. Yeah? This is not necessarily, it's called greedy decoding, but it's not necessarily a good strategy. Why? Because always choosing the next most likely token will result empirically into very repetitive text. That's one problem. But if you scale the model up, this problem goes more and more away. The second most important problem is when you produce text, you want it to be a little bit surprising. Because if you're taking the effort to read some text as a human, you want to be half informed, but half also in the comfort zone. Otherwise, by too much information, you don't even know where to put it. So text, very good produced text, should be half informative, half not so informative. It should have something new, but also things that you already know about. And always choosing the next most likely thing will produce very boring, very uninformative sentences from the human perspective. Therefore, it's not usually greedy decoding that people do. There's more complicated strategies like top P sampling, or now it's speculative decoding is very in, or beam search or other things. But it's a lecture in itself to talk about decoding strategies. So I will not. We will pretend now that we're doing this greedy decoding. We're just choosing via argmax the token that has highest probability, and we will choose that. And hopefully it's cat, maybe not. And we choose whatever the maximum probability was and put the token over there up, and then do this whole thing again. We apply our transformer layers, our linear layer, get probabilities, via argmax select the next most likely token, and so on and so on, and we continue until we run out of sequence length. Here in this visualization, I pretended we have a sequence length of 4 because it would have been a little bit of a long transformer to say the sequence length is 32,000, but usually in practice it's 32,000 or 128,000, or there's a model by Google that is going to 1 million or even 10 million tokens. So we produce tokens and tokens until we run out of sequence length, because after that we don't produce anything anymore, or until we produce a so-called stop token, or end of sequence, or end of sentence, call it how you want, EOS token, because during training we usually at the finish, at the stop of a sentence, so after the dot or the question mark or whatever, however a sentence ends, we append an end of sequence token, such that the model also learns that sentences also have to end at one point, right? You cannot just keep predicting and predicting, even though the model actually could. It could predict until the sequence length runs out. Yeah, and this is how a transformer decoder works. Any questions about exactly the decoder? Yes? Hmm? Yeah, so, well, I mean, transformers back in the days were trained on sentences because they had a sequence length of a maximum sequence length of 512. And there you kind of could fit 1-2 sentences, and they actually trained on 2 sentences, and then kind of that was it. But now, because we have GPUs of the size where you can say, let's go to 23,000 or 32,000, or even more, we usually don't train on the training is not done sentence-wise, it's done paragraph or even document-wise. And but still, at every end of such a document, you put an end of sentence to let the model kind of also finish after a while. So yeah, I mean, it doesn't really matter how you chunk your text and how large your text you define to be. It's a little bit of what you can do on your GPU. Yeah. Okay, thanks for the question. Yeah. Yeah, it predicts them autoregressive. So that's a little bit of a problem. During inference, you have to wait for the token to finish such that you can go on and predict the next token. But that's just a limitation during inference and not during training. During training, the sequence is already there, and everything that I done here sequentially, you can do in parallel, because it doesn't matter what the model will produce. We will pretend it said SAT anyway, so I can do all this training in parallel. This is why we can read entire Wikipedia during training, and we can, or very quickly, and much quicker than RNNs, and that's why transformers are so good. But yeah, so indeed, inference is slower. Yeah, so, and that's why there are a lot of techniques to speed up inference. One of them is called speculative decoding, which I was talking about, because, so what happens during inference, we need to decide of what the next token should be. And to have a super large transformer model of 175 billion parameters do its inference all the time, it takes a long time. It takes a second maybe until we produce 10 tokens. That's too long, let's say, and we're lazy and we want it faster. That's why speculative decoding looks at the probability distribution over here and says, okay, that was the next 5 tokens are very easy to predict, so I will not employ the large 175 billion parameter model to do my inference for the next 5 tokens iteratively. I will apply a very small model like GPT-2 of sizes of just 1 billion and not 175 billion, so 100 times smaller, and it will run considerably faster, and then you do this speculative decoding for the boring tokens, and then you will employ the large model for the complicated tokens again. So that's one way to do it, but of course there's a lot of research going on into how to speed up inference to make it fast, because users interact with ChatGPT and don't have time the entire day to wait for the answer. But you see, ChatGPT is not very slow. Like, it will give you a very good chunk of text in just a few seconds. So yeah, there's a lot of research there. Yes?
is ever more information of all the words that have brought to
yeah. 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 And I will paraphrase a very renowned linguist or a person in natural language processing called Raymond Mooney, who was looking at these things when they weren't so successful yet. And actually, they were still RNN based, but RNNs again just kind of summarize the meaning of an entire sentence in just one single vector. And he was saying you cannot cram the meaning of one vector of one sentence into just one vector. He was very against it. He was saying this is impossible. You cannot cram the meaning of one sentence into one vector, and he was wrong because you can. I mean, empirically he was wrong because, of course, in 512 dimensions there's not as much space as there's in 2048 dimensions, but there's a lot of space in 2048 dimensions to really cram the meaning of one sentence into an entire vector. And yeah, that's what happens. But also important is to know, at least for transformer decoders, it doesn't have to be the sentence of the meaning of the entire sentence. It just needs to be what is needed to know to predict the next token. To predict the next token is easier than to just to memorize or to summarize the entire sentence. But we will have transformer encoders who will do exactly that. They will summarize the entire sentence into just one vector, and it still works because 2048 dimensions are a huge lot of space to fill. Yeah. But it's a good intuition to have. You're very aligned with a renowned linguist and an NLP person. Yeah. Yes. Yeah. Yeah, so, okay, so that's, you opened up the can of worms. There's just the debate in linguistics and NLP since these things came out. And the idea is how much understanding is really there. If these models are trained on text and not on the world, they're trained on text and text talks about the world, but not necessarily. I mean, there's a lot of fiction that these models were trained on, yeah? And it doesn't have any means to say whether something was Jules Verne and Jules Verne talks about fiction, or there was a passage in Jules Verne which is really historically accurate. No way to tell it. It's just that, and it happens to appear that if you're training on lots and lots of data, there is a distribution of truth over there. Like, it's not impossible to discover it. There is something, but of course it's wishy-washy and a little bit smeared out and not as crisp as we want it to be. But yes, there's entire papers. Read the stochastic parrot paper if you want. That makes the case that if you train on just language, and which language is a secondary order representation of the world, it's not the world, then you will never get to true meaning, because true meaning is more complex than just the way in which we symbolize the world in a few tokens. And one way to overcome that is the whole endeavor of multimodality, where you don't have transformers look at just text input, but also at other modalities such as vision, video, haptics, whatever you can imagine, and then hopefully the view of the world will be more holistic. But yeah, it's a very long discussion to be had, but that's the short answer to that. Okay, I hope, yeah, one more question. I would argue that people disagree of how much understanding there is, and there's of course these diehard people who say it's no understanding whatsoever. I would say there's some understanding. If that understanding is very much aligned with how we understand things, that's very debatable and still to be discovered. But there's some understanding going on there, and there's no. I think it's very hard to debate that some things should be understood if you say the bottle will fall instead of the bottle will start to fly up to the sky. Some. Okay, good. Let's go to transformer encoders. which are basically another way to learn about language. And I will try to make the case of that it is also a very effective way to learn about language. And it's a little bit different to this autoregressive way of transformer decoders seeing it, because now for visualizing transformer encoders, I had to kind of double the sequence length, if you see, but this doesn't mean that the sequence lengths of encoders are usually larger than of encoders are usually larger than of decoders. It just means that I need more tokens to make my point. Yeah, and here the point is that we take a random 15% subset of the tokens in the sequence and replace them with the token mask. And we apply our transformer layers, and now attention is not masked anymore in this causal way. It's really bidirectional. It really looks at both directions. And the transformer layers do their things, and then we look into this representation with a linear layer, which we will call the mask language modeling head, and we'll map to logit space that it is as large as there are tokens in our vocabulary, so V, and then with a softmax we will map to probabilities. And then via argmax we can select which is the most likely token to replace this mask token. Yeah, this is how language is learned, but decoders, encoders usually historically did a little bit more, namely they also have a special CLS token. CLS stands for classification, and to the last representation of the CLS token, we apply another linear layer, so it's different weight than this, yeah? So it's a different linear layer, that's why we call it classification head, and we map to a logit space that is much smaller because it usually responds to a certain task that we put to the model. And the task that the BERT encoder had during pre-training was to decide whether the two sentences that it got as input are natural continuations of one another, or whether these two sentences come from very random places in the training data. Yeah? So usually in training data, you have sentence after sentence after sentence, and you can show it sentences that come after the other, and then you expect a yes. And if they, it's basically a binary classification. And if they come from disparate random portions of the training data, it is expected to say a no. And that's how it is supposed to learn the semantics and coherence between sentences. And also, coming back to the how much information can you cramp into a single vector, this vector needs really to focus and to summarize the entire sequence, yeah? So this vector here is way more summarizing than this token, because this token just needs to say what is the next most likely token. So if it's very focused, it's fine. But here, this token is very much a semantic summary of the entire input sequence, and that semantic summary you can use for other things. Like if you want a representation for just a whole sentence, this is a good place to look at. If you want diffusion models to know what the text is about, this is again a good place to look at, but about that another time. Okay, and the question is, how much language can we learn by just masking and masking 15% of the tokens? And the answer was quite surprising, a lot. Because there is this paper that analyzed the BERT model, the BERT encoder model, and looked at what is it that from going from input to output, the transformer learns in each layer. And it seems like the first layer learns very low-level features of language, such as part of speech. Part of speech means that you now know what is a verb, a pronoun, a noun, and many other things. Okay, so after the first layer focuses on that, and the next layer focus on more high-level things, which are, for example, constituents. Constituents mainly say that words belong together. So the red ball is basically a constituent. It's so of course it's composed of the red and ball, but now it's a constituent, and in this layer it kind of recognizes that. Then you go into even more complicated NLP structures, such as dependencies or semantic roles. So dependencies are basically that you know what's a subject, the predicate, and object. Semantic roles means that you're able to answer to who did what to whom questions, when and where. And then you go into coreference. Coreference are very long range dependencies in text. Like, for example, I can say Olaf Scholz is there and he did that and that. And then he was sad to know that the pronoun he refers to Olaf Scholz. That's coreference resolution. And it's a very long range dependency that you have in text. And so on. So if this reminds you, this hierarchical deconstruction of language reminds you of the NLP pipeline, it means that you're a natural language processing person. But if this reminds you of the hierarchical feature representation of CNNs, it means you're an image representation person. Because in image representations, you have your input image, and the first layer in a convolutional neural network also look at low-level features of images, namely edges or colors or other things like that. And then they combine these low-level features into higher-level features, and until the end, it recognizes the cow. Yeah, so it's very, very surprising, and people didn't expect that, how much language you can learn for just this stupid strategy. And of course, it's a stupid strategy for 10 sentences, but if you apply it on 1 trillion tokens, if you apply it on the entire internet, you're really good at language and learning very good stuff about it. Okay. Any questions about the transformer encoder? It doesn't differ very much in training versus inference. That's why I didn't make now a full-fledged distinction between them. Yeah. From the random number Jesus. Yeah, it's basically the random number generator that decides. So we have, let's say, L tokens in our sequence, and you take a random 15% subset by random. Good question. Good question. And I take a bit of content from slides that I prepared for later, but the idea was that, yes, people use this 15% because it shouldn't be too much, otherwise you kind of ruin the entire semantics of the sentence, and it shouldn't be too little, otherwise you don't have any masking. That's basically the reasoning that people had, and they stuck with this 15% for a very long time. And guess what paper appeared last year? I think it's last year or this year. Anyway, so quite recently. So these things were invented in 2017, and I'm now talking that 2023 or 2024, I forgot exactly the year, a paper came out which is called so they're doing text diffusion with discrete diffusion models. And then you think, oh, it's discrete diffusion models, it's something entirely different from the BERT model, and they never reference the BERT model, they don't say it's BERT. But if then you open the discrete diffusion model paper and look at what it does, it's just people that didn't, so they don't reference the BERT model, but it is the BERT model with a variable masking strategy, because the BERT model has this fixed 15% masking strategy. This discrete diffusion model has a varying masking strategy from 0 to 100%, and they show it works. So I have to answer to this question that people use 15% for reasons that are not necessarily principled, because you can go with a varying masking strategy from 0 to 100%, and you then call it a diffusion model, but it's still a BERT model with varying, yeah. So, yeah, there's no principled reason to that. Yeah. Oh. I think it doesn't look random to me. To me, this is an edge detector. This is a 45-degree weird edge detector. This is a little bit of a stylistic representation of what happens, but you have edge detectors. So really what CNNs discover is the classical image processing pipeline. You did first edge detection, you said something about colors, you did the Laplacian to look at blobs and stuff, and after you did that, then you try to get higher order semantics out of it. So no, to me it doesn't look random that a neural network can, so this cow is, it's a stylistic representation, but what you can really see in these features, if you look at doing car detection, you really can see wheels and doors and stuff. So it's really not random. Yeah. And again, this also looks random to a person that doesn't do NLP, but if you're a person that knows what the part of speech is, then it doesn't look random anymore. No. Okay, cool. now that we're experts in encoders and decoders, we will go into encoder-decoders, because you have maybe heard of autoencoders in this lecture before. So if we have an encoder and we have a decoder, why not put them together and make kind of a autoencoder-ish structure out of it? And yeah, this is what happens in our encoder-decoder architectures, which are basically working in the following. Here, everything flows from bottom to top and not from top to bottom, because I stole this image from Jay Alamar, and now he visualizes things usually from bottom to top. And here the idea is to have an encoder get its input, do its encoder thing, compute better representations for the input, and then the decoder does its decoder thing. So via self-attention, it attends to what it predicted so far, but plus it also kind of gets an additional history, namely via keys and values. It gets access to the representations, to the output representations of the encoder. So so basically it looks at its own input. If it has some input at the beginning, of course, there is no input to the decoder because the decoder didn't produce anything. So it just looks at what the encoder summarized about the sentence. Then it produces the next token. And then after it predicts the next token, it looks at the previous history that it itself produced, because autoregressive, but also the history that the encoder produced and summarized about the entire sentence. And because here the attention goes from, self-attention is when the attention key, keys, and values come from its own, from the own tokens. But now, because the key and value come from another, from the encoder, it's called cross-attention. Yeah. And why do we have such a architecture? Well, it's very good, as shown in the example, for machine translation, because machine translation is the natural language processing task of translating a source language into a target language. Here it's French and English. And the good thing about keeping it in encoder-decoder separated is that the encoder can focus on just the French, and the decoder can focus on just the English. So the job of the encoder is, it's a little bit like, autoencoders, because they also make a nice semantic representation in that bottleneck. You can imagine this is the bottleneck. Here we summarize the meaning of the sentence in French, but and because it's training jointly with the decoder, this meaning is hopefully as language agnostic and as language overarching as possible. So we really summarize the meaning of the sentence and not the language. And then the decoder can go on and focus of producing the language in English. Yeah, and that's why an encoder-decoder architecture is good for this task. The natural question which arises is, why do we have 3 types of models and not just decoders? Decoders could do it all, right? Well, not quite. They all have their strengths and weaknesses. Encoder models, they're very, very good at summarizing or cramping the meaning of an entire sentence into just one vector via this classification token that has to make a verdict about the entire sentence. So if, for example, you get a sentence and you want to decide whether it's a positive or negative movie review, then that classification token is the place you look at, because it has summarized the meaning of the entire sentence. Then, if you want to summarize the entire sentence because you want to do semantic search, so if you want to implement a search engine, you want to be better aware of, or to summarize in just one vector what the meaning is of the query of the user, such that with that one vector, you can go and search for similar vector in your database, and that's very helpful in retrieval augmented generation. Or diffusion models, when they produce images from noise, they also need conditioning or information injection about the meaning of text if you want to do text-to-image diffusion models. So usually the last representation of encoders are a good thing to use for text-to-image diffusion models for text representation. Just foreshadowing, I guess, next lectures about diffusion models. And I would say, and here, that they're not yet great at producing language from scratch. And I added this yet for the reason of the paper I mentioned before, because of the question, that yes, I mean, encoders usually had this fixed 15% mask rate and didn't go and train between 0 and 100% masking. But since last year or this year, I forgot which year, the people have been focusing on, reinventing BERT, but calling it diffusion model and making a variable masking rate, which makes the model much better at producing language from scratch. Yeah, so that's why I add yet. So if you think about BERT, no, BERT is not great at producing language, but BERT could be a good language provider. It's not yet, but they are great at replacing missing words. So if you think of any task where you have a fill-in-the-blank task, BERT or encoders are usually the way to go. They're very good at filling in the blanks because they're trained for it. Then decoders have the upside of being generative models of language, and you cannot say that about encoders. What does it mean to be a generative model of language? Well, to predict the first token x1, we kind of predict the probability of the token x1 given no history, so it's just the probability of x1. But if you want to predict the probability of the next token x2, we predict the probability given the input, given x1, given the first token that was produced. So, to summarize, to predict the nth token probability, we compute its conditional probability based on what was previously said. And what is this? Does somebody recognize this formula? What does it represent? If we, chain conditional probabilities like this? Yeah? Exactly. Joint probability distribution is the joint probability of all tokens in the sentence. So basically, we have computed the probability of a sentence. So if you have sentences or paragraphs or whatever and documents lying around, and you want to compute the probability that something like that occurs on the internet, you train a model on the entire internet, and then estimate with that model trained on the entire internet the joint probability of that paraphrase or paragraph or document that you have lying around. And that's what it means to be a generative model, is that you really can compute the probability that a data point will occur. And it makes great chatbots for reasons we will get to maybe some other time. But the idea is that encoder-decoders are a mix of both encoder and decoder, so they bring the upsides of both encoders and decoders, but they also bring the training instabilities and the complexities of both models, meaning that they are larger to scale. So here we can look at the evolution tree of such models. You can ignore this part because they're more classical neural NLP stuff I will not talk about. But these are the encoders. These are the encoder-decoders in green, and here in this blue-grayish, they are the decoders. And you see encoders and decoders emerge at quite the same time. But progress for decoders was slow at first. Encoders exploded. It's like there were many, many encoder types you could use. And but after a while of doing encoder stuff, the progress kind of stopped in 2021. Why? Because in 2021 with GPT-3, people realized, oh, decoders, you can prompt decoders. And they can make ChatGPT basically for reasons we will see another time. Meaning that this branch exploded, and when I mean exploded, I really mean exploded, because this is a really tiny little subset of all the language models that are out there. And the progress of encoder-decoders was always there, but always slow. So it took a long time until people figured out how to make these things train stably. And also, as you might have encountered with autoencoders, there's this problem of it's called posterior collapse. That if you have a very strong decoder, what your encoder delivers doesn't really matter. The decoder will be able to produce English anyway from French, even though French was not well summarized. So the idea is that these things are harder to scale. These are much easier to scale, and that's why it's going on so well for them. Okay, and because I didn't get that as far as I was imagining for today. Maybe I can come another time to finish. I wanted to basically say that the most successful architecture of today is, of course, decoder transformers, and that's why when people say large language models, they mean decoder transformers. And the question is, when do we call a language model a large language model, and when is it a small language model? So the idea is that you will never see me say any number too large, because the large is very context dependent. It depends whether you're GPU rich, you have a few hundreds of thousands of H100s, or whether you're GPU poor. If you're sitting with just one 3090, then anything is big to you. And if you're GPU middle class, you kind of can do a little bit from both. And L in LLM is not a time invariant attribute, because we have the thing that according to capabilities of what the model can do, the 175 billion parameter of 2020 is the 7 billion parameter of today. So, kind of 2 orders of magnitude less parameters bring the same capability. And the notorious example from last week is that the Llama 3.3 model came out, and at a size of 70 billion, it can do what the Llama 3.2 could at 405 billion parameters. Yeah, so it's not a time invariant attribute. That's why I will not give any parameter numbers for all these things. And it's always the case that Moore's law, it kind of continues to go on, and the GPU rich gets GPU richer and can scale up to even more parameters. So when we say LLMs, I just want to say autoregressive language models, and that's it. So yay, we did half of what we wanted. We now know what was established 2017, and if I get the chance, I can tell you maybe next time what was happening since 2020 and how do these things really reach the level of ChatGPT, because it's what happens here. So thanks for your attention. I think the time is up, but I will be here for questions if there are any. Thank you.